Welcome to today's lesson, and in today's lesson we are going to look at our topic, which is digital electronics. It's an interesting topic where we shall be looking at some kind of continuation from electronic devices and components that you looked at when we were looking at the topic of electricity. So your teacher is, as usual, teacher Ahebo William, and like I remind you, please subscribe and like our channel, YouTube channel, which is teacher Ahebo William. You can always search it and you'll find there very many lessons of physics, and you can like and maybe comment. You can supplement where needed, and you can as well reach us on WhatsApp, the number 751407158. We shall be able to be in touch. Let's dive into our today's menu. We shall majorly look at not a lot of things. Under this topic, we only look at two areas, major areas. One is potential dividers, and then the logic gates. So let's start by looking at the introduction bit of it. When you are looking at the topic of electricity, you looked at the components that make up an electric circuit, and some of those components, maybe to remind you, if you to recall, you looked at resistors, diodes, thermistors, LEDs, or light emitting diodes. That was under that topic of electricity, or the one which was known as voltage, resistance, and Ohm's law. And maybe you might have had a chance to look at the real components, or you just looked at their symbols, but this is how some of those components look like. This is a fuse, a transformer, an inductor, a capacitor, a resistor. If you open the circuit board of either radio or any electronic component, a phone, a charger, you'll see most of these components, you'll see them in there. So some of them, they are even indicated on the board. On the board, you might even find that they indicated their symbol is there. This is a potentiometer. Another name for a potentiometer is a variable resistor. That is another name. We shall see what it does actually, because this does exactly what we are going to talk about today: potential division. It divides potential, like we are going to look at it. A thermistor, this is how a thermistor looks like. This is a resistor network, which has very many resistors in there, and therefore it can vary, or it can divide voltage depending on the need. The varistor, etc. You looked at all those electronic components and even many others that we've not mentioned here. So why do we now talk about them, or what is their role? These devices, we all agree that they help us to make the digital electronics, like the phones, the TVs, the chargers, mention it, all those electronic components that we use in our daily lives. They even, like the bulbs you use these days, they are LEDs, most of them. So these components, that's what they do. But like I told you, in this area we are going to focus majorly on the potential dividers and what they do. Now, if you want to now know what are potential dividers, or why are we looking at them, I want you to think about components in a radio or a TV or a phone. When you look at that, let's say television, or let's say radio, something that most of us could have come across, you realize that in there are very many components: diodes, resistors, you have their transformers, you have their LEDs, light emitting diodes, those small bulbs which will be producing light. Now you realize one thing is that now you'll find that this radio, you just put in dry cells. Which dry cells? They may be 2, they may be 3, depending. Which dry cell is 1.5 volt each. If there are 2, that gives you a total of what? 3.5 volt, 3.0 volts, right? Now, don't you think, aren't you wondering how comes these different components that I'm having in this radio, they are all functioning, yet the voltage that I have entered is 3 volts. And remember, not all components are supposed to work at 3 volts. Then how is it possible? And that is where this part, the potential divider, comes in. Think about it even when you look at a TV. When you plug that TV in a socket, you may already be knowing the socket is supposed to be at which voltage? Between maybe 110 and 240 volts, depending. Let's say it is at 240 volts. Do you think all the components in that TV are supposed to work at 240 volts? No. Some of the components may be needing lower voltage, while others they need higher voltage. Then how does the TV manage to do that? Yet it is only connected to one supply, which is 240 volts. So that is where the potential divider comes in. Like the name says, potential divider. Its role is to divide the potential that is supplied. So from the scenario there, you realize that the input voltage is subdivided to suit the different components of a device. Like we said, if we have a component that needs a voltage less than 240 volts, and there is another one which needs maybe 180, there is another one which needs maybe 20 volts, the potential divider will do that. It will divide to make sure that each component gets the voltage that is needed. So let's dive into what potential dividers are. Potential dividers, let's look at a circuit. Look at this circuit here. If you look at that circuit, I know this is something that is very simple for most of us. If you've looked at the topic of electricity, you have the voltage which is being produced or provided by a battery, which is the input voltage, or this can even be the voltage which is being supplied by the socket. You see that? Now you have here your two resistors. Now if I ask you a quick one, these resistors are connected in which type? Which type of connection is this? Good. This is a series connection. Very good. Now under a series connection, if I'm to ask you, what do you know about a series connection in terms of current? So you agree that current in a series connection is the same. The current passing through this resistor is the same current passing through this. It does not change, okay? But the voltage changes. The voltage across this resistor is not the same voltage across here. However, what we know is that this voltage supplied here should be is the same for is supplying all of them, but the voltage across each one of them is different, okay? It is changing. So if I'm to determine the current, how will I get it? First of all, before I determine the current, I need to know what is the resistance in the circuit. So since it is a series connection, the total resistance will be the resistor R1 plus R2. I think this is not new to you. You must have looked at it under voltage, resistance, and Ohm's law. Then from Ohm's law, which it says that voltage will be equal to current times resistance. So if voltage is current times resistance, and we have already known that our resistance here, the resistance in the circuit will be R1 plus R2. Therefore, how can I determine current? Current will be given by, so from that statement, if I substitute in R1, resistance is R1 plus R2. So voltage is equal to IR. Remember, this is total resistance. So therefore, my current will be given by voltage, the input voltage divided by total resistance, okay? That is the current passing through the circuit. The current passing through resistor 1 and the current passing through resistor 2. So if I want to determine the voltage across resistor 1, how will I get it? Still using Ohm's law, voltage across the resistor 1 will be current passing through that resistor times the resistance, which will be V1 is equal to I times R1. But we already know what the current is. Current is given by this input voltage, which is given in divided by the total resistance in the circuit. So if I substitute it in here where there is I put there its expression. meaning the voltage across resistor 1 will be given by what? Input voltage out of total resistance multiplied by the resistor R1. Or in simpler terms, as a final expression, it will be this. If I simplify it, because V times R1 is VR1. So you realize that the voltage across that resistor will be given by, that resistor divided by total resistance in the circuit times the input voltage. This is the same expression, members. Let me hope it is not confusing you. It is just the same expression. I'm just trying to rearrange. So it means that is how you will determine the voltage across R1. Now you observe one thing, that if resistor 1, the value of R1 increases, then the voltage across it will also increase. If R1 decrease, the voltage across here will also decrease. You're already starting to get the picture now of what happens in a phone, a charger. That if the voltage is needed to increase, then the resistance will be increased. If the voltage needs to be reduced, the resistance will be reduced. You're already seeing that, okay? Good. Now, how about the voltage V2? How can we get it? Someone with a sharp mind must have already seen it. That similarly, looking at the same circuit, the similar circuit, still the total resistance is still the same. The voltage will be gotten by that. Therefore, V will be I R1 plus R2. Therefore, current will be the one we had already gotten. So using Ohm's law also, we now know the current passing through resistor 2. So using Ohm's law, voltage across 2 will be equal to current which goes through times this resistance. So it will be V2 is equal to I times R2, sorry. So if we substitute for the current, which we already know its expression, it will be that will give me voltage V2. So if I can just rearrange it, and therefore still to get voltage V2, I just need to get the resistance of that resistor divided by total resistance in the circuit times the input voltage. Okay, that is how. Now this is what we call the potential division. We had one voltage which was coming in, but by help of resistor 1 and resistor 2, we have got two voltages coming out. Meaning, I need to choose which voltage do I need to use. Imagine if I had connected to my socket, which was 240 volts. By the help of these components, I'm ending up having different voltages. Here I may be having maybe 30 volts, here I may be having maybe 150 volts, you get? So I can decide, depending on the voltage I need, that is where I will connect. If I'm having a component that cannot use more than 30 volts, I will connect it to the voltage which is smaller. If I'm having a component which needs a bigger voltage, I'll connect it to the voltage which is bigger. So you realize that I'll have divided the voltage which was injected in. I know some other people may be thinking, but now teacher, we looked at transformers. How about we use a transformer to reduce the voltage if it is big? Now remember, will you keep putting everywhere a transformer because you want to reduce for every component? No. So that is why a potential divider becomes now useful. Okay, but that is smart of you to think like that as well. So let's look at we look at the alternative. We may have a circuit in this way, whereby I'm supplying here my voltage, the input voltage, but I'm having here my resistors, my two resistors, R1, R2. Now these resistors, it can be like this. This may be like a rheostat, whereby I'm varying, or like a potentiometer, for example. What I'm saying, a potentiometer, I'm varying. If I extend there, the resistor there is reducing, the resistor R1 is increasing. If I extend the connection here, then R1 you see will now be small, whereas R2 will be very big. So I can vary it here, meaning I'm still creating two resistors, out of the same. And but let's say this is the TV I'm connecting on this resistor, or a loudspeaker. Let's say, for example, the speaker. Now this speaker I'm connecting to this circuit, it may also have its own resistance, which we are calling R of the load, because the speaker in that case is the load. So when I connect it here, you realize now the entire circuit, I'm not having only two resistors, I'm now having the third resistor. But this third resistor is in parallel with R1, okay? It means if I want to get the total resistance in the circuit, total resistance will be resistor R2 plus the total resistance between these ones, or what we call the effective resistance between R1 and RL. Remember, these two are in parallel connection. They are not in series with each other. Now, it means before I get the total, I need to first know what is that total resistance of these two. So from our previous knowledge, we know to get total effective resistance when I have two resistors in parallel, I just say one out of that effective resistance, it will be equal to 1 over R1 plus 1 over RL. That will give me the effective resistance between these two. And therefore, if I go on to simplify by taking the LCM, I believe you're now very good in mathematics. If I'm to get the LCM, you agree with me, it will be like that. R1 times RL. Up there you'll have, because when you get this divided by R1, you'll remain with RL. So RL times 1, RL. Get this divided by RL, you remain with R1. R1 times 1, it will be R1. So you have it like that, and therefore if you take this up, this one will also go up. So meaning the other one will go down, which gives you the effective resistance as RL R1 over this. So it means now I'll have gotten my total resistance. If this had values, if this was maybe 2, this is 1, or this is 10, this is 30, I can now substitute in those values and I'll be able to get the effective resistance. Okay? Now it means I'm able to get my total resistance now, isn't it? Because after getting that answer, I can substitute it in that expression. Remember, you'll be knowing the value of R2 as well, so you'll get the total resistance. Therefore, if I want to get the current passing through the circuit, it will still be from Ohm's law, V is equal to IR. So V is equal to I times R. So it means my current will be input voltage, which is this voltage here, divided by the total resistance. Remember, you'll have calculated the total resistance. Okay, don't confuse the two. We have the total resistance, which is for all the three, but we also have the effective resistance, which is between these two. So when you get that effective resistance, we add it to R2, it gives us the total resistance. So you'll have gotten my current, and implying if I want to determine the voltage across resistor 2, or the voltage across the load, this load here, I now know the current which is going through these sections. So since I know the current going through R2, so voltage which is voltage V2 here will be given by I R RE. Sorry, this is supposed to be R2. Excuse me there. It is supposed to be R2. So, but since we know already the I, the current I here will be, you substitute in its expression, which is V over RT, and therefore you'll be able to determine the what? Your voltage. You see that? That is how the potential dividers work. Now, if we look at the applications, like I've already told you, you're already seeing their uses. One major use is they are used in volume controls. Remember what we said. If you look at this expression I'm showing you, it means that if I want a bigger volume, it means I need the voltage in this area to increase. So what do? I will increase its resistance. If I want the smaller volume, reduce its resistance. So that's why when you're increasing the knob of the volume or when you're reducing it, you are basically increasing or decreasing the resistance of the speaker across the speaker. So as you're increasing it, the voltage there is increasing, that's why the sound will be big. As you decrease it, the voltage is maybe reducing, and the resistance is reducing, and hence the voltage will be reducing, and therefore you have smaller volume. So that is one use of the potential dividers. Another use is they are used in sensing devices, e.g. automatic lighting systems. We are going to look at an example. They are also used in thermostat switching systems. You've looked at a thermostat, for example, how it works. Some of those systems, they use potential dividers to switch on and off, like we are going to look at an example. Now let's look at that an example here. We see how it looks like. A thermistor is used in automatic cooling system of a refrigerator to switch on the cooling circuit when temperatures inside the fridge reaches a certain value. The fridge is connected to a 6-volt socket, and it is known that the cooling system of the fridge switches on if the voltage in its circuit is above 5 volts. You see that? That if the voltage in the cooling system is above 5 volts. Now they are saying if the cooling system has a resistance of 5,000 ohms and the thermistor's resistance varies with temperature as shown below, that this is how the thermistor's resistance will be. When the temperature is 2 degrees, its resistance will be 1,500 ohms. If the temperature is 3 degrees, the temperature of the thermistor is 1,000 ohms. The resistance, sorry. If the temperature is 4 degrees, the resistance of the thermistor is 500 ohms. If the temperature is 5 degrees, then the resistance of the thermistor is 100 ohms. So what do they want us to do? They want us to determine the temperature at which the cooling circuit will be automatically switching on. That what will be the temperature that will enable this circuit to switch on? At which temperature will the fridge automatically go back on when the temperature reaches a certain value? Remember, they've told us that that switch goes on only when the voltage in it is 5 volts. So it means we need to determine what will be the voltage in the cooling circuit. If this is the circuit, for example, look at it in this way. If this is the circuit, they've said the fridge is connected to 6-volt socket. It has a thermistor here, then the cooling circuit. Now a thermistor has its resistance, the cooling circuit also has its resistance. The cooling circuit has a resistance of 5,000 ohms. The thermistor has a resistance which depends on temperature. When the temperature is 2, its resistance will be 1,500. When the temperature is 3, its resistance will be 1,000 ohms. When the temperature is 4, its resistance will be 500 ohms. When the temperature is 5, its resistance will be 100 ohms. So we need to know at which of these resistors will enable the voltage across the cooling circuit to be 5. Okay? So let's dive into it. We see how does it work out. Let's look at it. Remember, these are our values and this is our circuit. So if we were given that we know to determine the voltage across here, it will be given by the resistance across the cooling circuit. RCC means resistance of the cooling circuit, out of since these are in series, total resistance will be R1 plus R2. So this is R of the thermistor, R1, R thermistor plus R of cooling circuit. Then we multiply it with the input voltage. Okay? So, but we have different resistances of the thermistor. Now at 2, these are the resistance of the cooling circuit is 5,000, and the resistance of the input voltage, the input voltage is 6 volts. So at 2 degrees, what will be our temperature in here? Using that equation, we see that the resistance of the cooling circuit is 5,000 times input voltage, which is 6, out of, at 2 degrees, the thermistor has which resistance? 1500. Plus resistance of the cooling circuit, which is 5000. We get our voltage of the cooling circuit at 4.6 volts. Okay. How about at 3 degrees? What will it be? At 3 degrees, automatically, you'll have to substitute in now. The resistance of the cooling circuit is not changing. The input voltage is not changing. What is changing is only the resistance of the what? Of the thermistor, which will now be 1000. So if it is 1000, then what will be our final answer for voltage? The voltage across the cooling circuit now will be 5 volts. But remember, they told us the switch will go on when the voltage is above 5. So this is not yet above 5. So if we go at 4 degrees, we know the resistance of the thermistor is now 500, implying that the voltage, the final answer for the voltage across the cooling circuit will now be 5.5 volts. So it means at this point we see the voltage is now above 5, meaning that this cooling circuit will now switch on because the voltage has gone above 5. Okay, so therefore the cooling circuit will automatically switch on at 4 degrees Celsius. Okay, yes, so that is an example of how a potential divider can be used in an automatic system. We see that the automatic switch is waiting for the voltage to reach that value so that it goes on. But how is it working? As the thermistor's resistance varies, it is enabling the potential divider to keep on varying the voltage, and as a result, until it reaches the value which is needed, then the switch will go on. So if you've picked something here, then you'll discuss this with your colleagues. The question for the discussion goes like this. Entebbe Expressway has street lights that automatically go on and off by using an LDR, light dependent resistor, connected to the sensory circuit. The switch circuit is of 10 kilo ohms and only goes on when the voltage across the sensor is 230 volts and below. That it will go on when the voltage is 230 volts and below. If the entire system is connected to an input mains of 240 volts and the light dependent resistor's resistance resistance varies with the time of the day as shown below. That it varies with the time of the day as shown below. Now this is the time of the day. This is the light dependent resistor during dry season, then during wet season. During dry season, it is at 5 p.m. the light dependent resistor has a resistance of 50 ohm. At 6 p.m. it is 100 ohms. At 6:30 it is 200 ohms. At 7 p.m. it is 434 ohms. At 7:30 it is 490 ohms. Whereas during wet season, at 5 p.m. it will be at 100 ohms. At 6 p.m. it will be at 220. At 6:30 it will be 434. At 7 it will be 500. At 7:30 it will be 700. Okay. Now the task. You help determine the time at which the lights will go on when it is dry season and when it is rainy season. Okay. You have to determine, use your calculation and determine at what time will the lights be going on, switching on. Remember, they've said the condition is they only switch on when the voltage reaches 230 volts or below. Okay. So you need to determine in dry season at what time will it be switching on. In a rainy season, at what time will it be switching on. Okay. If this is your sample circuit, like this is the light dependent resistor, the street lights are connected 240 volts, then this is the automatic switching circuit. For you will allow me, I end here this part. Follow now, you can watch out for part 2 where we are going to be talking about logic gets. Thank you for attending and listening.